I will talk about this topic, which is a recent work together with Andrea Braides and Lorenza Delia. More or less what I would like to say is something about the past, because the origin of this problem is strongly related to what I did when I was just a postdoc, young researcher. And, but more recently, thanks to Andrea Braides, I met this topic of non-local functionals, especially the type of convolution type. So we'll talk a bit about that. We will focus on what I want to say, this main result with applications to homogenization. So once upon a time, it means that when I think about the past and my beautiful time when I was a student, it was the 70s, 80s, and as a mathematician, of course, I met these problems on perforated domains, and mainly two problems like the cloud of ice problem and the problem of insulating inclusions were the starting point of several researches. So the idea, I want just to recall that for somebody who may not be, let's say, strictly related to them, if I have this such domain on the right, which is a conductor with some inclusions, either the inclusion may be filled with ice or may be filled with some insulator. I am interested in the, let's say, evolution of the temperature of this conductor under some heat force. And the two kind of problems correspond to different boundary conditions at the interface. So if there is ice, it means that I have fixed the temperature of the body at interfaces, and I have a Dirichlet problem. If I have insulating inclusions, then I have sort of Neumann problem, because I prevent the derivative, the normal derivative of the temperature to be non-zero. And so in the setting of PDEs, if the conductor is homogeneous, the problem can be described by the Laplace equation, the Poisson equation, with these kind of boundary conditions that I mentioned before. And epsilon is a parameter that takes into account the fact that we have these many inclusions periodically distributed and with a certain size that can be small. So the interest of the problem is to study the case where there are many inclusions and the radius, the size tends to 0. And these kind of problems can be seen also as, let's say, problems, minimum problems for integral functionals. Both of them are non-equicoercive in the sense that these, the integrals are settled on, computed on perforated domains, which are variable. And in this notation, the minimum of this, let's say, u in x of omega epsilon, it means that we incorporate the, let's say, the boundary conditions in the space. Laplacian, so the gradient u squared with the more general function that may have some growth, and we assume periodicity with respect to the space variable. With period 1 here, q is the unit cube of Rd. So what I will do, we will focus only on the case with Neumann boundary conditions. And so one of the popular approaches to this problem was that of extension operator. This is not the only one. For example, by Haller and Murat, they solved this kind of problem without using extension techniques. And later on, several techniques were developed. So with, in the context of Sobolev spaces with respect to measures and thanks to Zhirkov and others. But this approach with extensions was the one I met when I was young, and then I have particular attention to this. So in the pictures, the second picture on the right is due to a book taken from the book by Doina Ceranescu and Janine Sager-Bolin. They show two typical situations. On the left, the balls are the isolating inclusions, and they are disconnected. In the right picture instead, the conducting part are the cylinder, the network of cylinders, and the insulating part may be connected. So connection, in this case, connected insulator is allowed. And so in both cases, the solutions of the heat equation may be extended either to the whole set or to a smaller set, slightly smaller set, keeping, let's say, bounds for functions separate than for gradients. So this is very important to, let's say, get estimates that are, let's say, stable under rescaling. And in this, getting these separate estimates, it plays a role, the connectedness of the domain and the Lipschitz continuity of the boundary. And once the solutions are extended, then since the heat source is fixed, there are natural a priori bounds on the solutions that, let's say, are gained by the extensions. And thanks to the Rayleigh compactness theorem, these solutions are compact. And then it is possible, let's say, to study the limit problem. So this is more or less the idea. And what I want to remark is that in the case of disconnected insulators, the cell, the periodicity cell on the left is already a nice set in the sense that the boundary is smooth and the, let's say, the connected part, the conducting part is a connected set. Instead, in the general case, both properties may be lost in the sense that the conducting cell, which is here, may be disconnected. So the gray part is the conductor and the white part is the insulator. The conductor may be disconnected and may be singular at the boundary, even if you enlarge the cell. So these are technical issues, but they are very important to allow the construction of the extension operator. And in any case, in both cases, one can extend the functions, and the result does not depend on how the functions are extended inside, but just on the possibility to extend with this proper estimate. So the classical results in the two geometries are that of Ceranescu, Saint-Jean-Paulin. So if the perforated cell is nice in the sense that it is connected and has Lipschitz boundary, then there exists a linear and continuous extension operator from H1 omega epsilon to H1 of the whole set, and such that the three conditions are satisfied. The first condition just says that it is an extension, so the function is not modified inside. The second condition tells that the operator is continuous, uniformly continuous in L2, and the third one gives the estimates for gradients, which is something for us essential. In the case of the geometry, the more tricky geometry, it is not possible to get so nice result, but a little bit weaker in the sense that we can extend only to locally W1P functions. And also the gradient estimates, the number 3, cannot reach the whole set, but just a slightly smaller set. But let's say this notation omega r means that these are points inside at a distance larger than r. So in this case, just let's say a factor times epsilon. And that's enough to proceed then with homogenization. So this is what we are, let's say, our reference result to start with. So now we consider non-local functionals. There are various, many phenomena that are governed. They have some non-local properties. For example, a situation where the diffusion is faster in some part of the domain and slower in another part, or fluids that propagate faster in a part of the domain, like, for example, in blood vessels than in the other part of the body. Problems with in material science, like, for example, crystal dislocations or phase transitions that have a sort of non-local behavior. And this is a topic that I never studied. And in fact, I met recently, but I noticed that this is not a new topic. I noticed that the next two talks have this keyword, non-local, both the one by Nicola Fusco and that of Riccardo Scala, non-local problems. So it means actually now there is a sort of revival of this topic from different points of view, but the study of non-local problems dates back to at least the 90s and even before, because of course non-local functionals appear in the Gagliardo semi-norm, in the definition of fractional sorted spaces, in the definition of the fractional Laplacian and other operators. And then in material science, for example, in the problems of image segmentations, let's say described through the Manford-Achard functional, there are several approaches of approximating such functional in non-local ways. Another kind of problem is that of phase transition problems with non-local approximations. See, here, I'm sorry, I mentioned just very old papers because the complete literature is so wide that, of course, I would forget names. And so I prefer just to give very old references, just to say that this is well-established topic of research. And the last set, let's say, mentions about relaxation, Dirichlet forms, homogenization of non-uniformly coercive functionals. The last three topics are more in the opposite sense. So they start from local functionals, and in the limit they get some non-local phenomena. So there are the two sides. So what we will do now, we focus on the case of non-local functional of a special type that we call convolution type, because they look like some sort of convolution integral. And they are designed in such a way that the limit will be a local functional. So actually there are two variables. There is an integral in two variables, but in the limit, in the sense of gamma convergence, the limit will be a classical local functional. So here they look like the Gagliardo semi-norm, provided this kernel has certain assumptions. So everything depends on what is this function A. And another feature is that here we act on perforated domain. So it's not a fixed omega, but omega intersected some epsilon E. And here we reproduce the same assumptions of the extension theorem that I mentioned before. We have a periodic set connected with a good boundary, with a Lipschitz boundary, and we want to study the limit of these functionals. The case with growth 2 and with the geometry with disconnected insulator was studied last year by Braides and Piatnitsky, and the work we did is inspired by them. So what happens, what is the heuristics of this kind of functionals if the domain is has no hole? So I go back just for a minute. We have this integral here, and the domain is fixed. It is just omega times omega. So if we take, for simplicity, just a smooth function, u, C1, for example, and we rewrite u epsilon u of y as with a Taylor expansion. So the difference u of y minus ux is replaced by this term. So the gradient of u times the increment. And then a change of variable. So taking, for example, y equals x plus epsilon xi. For any xi in RD, so the change of variable, so we have double integral. The second integral is on this set omega epsilon xi that for some choices of xi and epsilon may be empty, but when epsilon goes to 0, it becomes non-empty. Cancellations of the red terms. And then in the end, what is remain clearly just the double integral on the blue set. approaches a functional of this type. So our limit should look like this, more or less, which looks like a norm of the gradient of U, but perturbed by this kernel A. This idea is made rigorous in the paper recent paper by Alejandro, Ansini, Braides, Piatnitsky, and Tribuzio, where they study general functions, more general functions of this type, and they prove by gamma convergence that these are really approximation of this sort of LP norm of the gradient. And from this, it's clear more or less what should be the good assumptions on the function A to make sense, to give sense to this function. First of all, we want that this functional is finite, and so this requires some decay of A at infinity, in the sense that we want that A times psi to the P, for example, is finite when integrated over RD. So this is one condition to make the functionals and the limit finite. It is reasonable to assume this. And another condition which is one wants is that when one follow the approach by gamma convergence, usually we want that functions with bounded energies are compact in some space, possibly in a strong sense. So not with convergence sometimes is too weak for us. So in order to get this compactness, one requires some coerciveness condition, which means that from the bound on the energies, we want to gain some bound on the functions, on the state functions, let's say. And the condition that they ask, the authors that I mentioned before, they ask that this kernel has a lower bound, at least on a fixed ball. Of course, if A is 0 everywhere, we have no bound, and the U epsilon may be anywhere. But this is enough to get a good compactness property. More precisely, they prove this, the compactness result, which is in a sense, it replaces the Relic-Sobolev theorem that we use in the classical setting when the functions are functionals are local. So the statement is the following. Let's take this dr. The notation D reminds to me the diagonal. It's a neighborhood of the diagonal. So that's the points, pairs of points that are at a distance at most R. So the diagonal and a neighborhood. The theorem states that if we have an open set with a smooth boundary and a family of functions that are bounded in LP plus this condition 4. This condition 4 in a sense replaces the bounds on the gradients, but here there are no gradients because these are only LP functions. And this is more or less the quantity that we have seen before, only, let's say, 4 psi bounded by a constant R, and in a set which is a retracted set of, let's say, it's slightly inside the given set omega. Provided this is true, then any sequence that has this property is compact in LP, and the limit in LP log, let's say, and the limit is W1P. So more or less, under this condition, condition 4 plus the LP norm bounded provides the same as the Relic-Sobolev theorem. So that's why they use these two conditions on the function, the kernel A. So now we go to our goal. The goal is to repeat what they do, but perforating the domain. And this was done with nice disconnected holes by Braides and Piatnitsky. So we tried to repeat the argument of extension operator. So this is the main result that we prove, this together with Andrea Braides and Lorenza Delia. We take E, periodic connected with Lipschitz boundary, we take an open set omega, and we prove that there is a constant depending only on the Lipschitz properties of E, and another constant C0, K0, such that for all epsilon, we can extend P to perforated, from LP of the perforated set to LP of the full set, and satisfying all these properties. Clearly, extending from LP to LP is not a problem because we can always extend by 0, for example, But this is not good for getting compactness of the sequences. That's why we have to produce some special extension. And so the first condition is just that we extend. So the first condition is just that these are extensions. The second condition is just that there is a continuity in LP of the extension operator. And the new part is the blue one, where we control the increment of the extended functions with the increment of the original one. In this blue inequalities, there is a red part, and the red part is important because it's the one that depends on the connectivity of the domain. Actually, we do not want just to compare increment with increments, but we want that for all R, even small r, we can, let's say, control increments on a neighborhood of the diagonal. This is something that reminds us, let's say, control on gradients. And this is the reason for which, let's say, this estimate will be useful for our functionals to get equicursivity and compactness of the energies. The construction follows the scheme of the old paper, so the case of local functionals. And the steps are, so first, just to solve problems with lack of connectedness of the cells, then extend from a connected component of a larger perforated cell to a small but full cell to Q, and then glue all these extensions using the periodicity and using a partition of unity built in a periodic way. And then rescale, of course. So this is the standard scheme. And the first step is really, we use this result with Acerbi, Dalmaso, and Percivale. So if we have a periodic set, which is connected and with Lipschitz boundary, it is always possible to find a value K for which, let's say, the perforated cell, in this case, we need 3Q, the cube of psi 3 intersection E, to be contained in a single connected component of a larger cell. And this component, which is in the picture, the gray part in the big cube, it may have a bad boundary here, but it has good boundary in this area, in the sense it has Lipschitz boundary in the part that we need when we build the extension. So this is, we use this result, and this is a new part done together with Lorenza and Andrea. So there are these three steps. First, we extend from a set B to another set omega. Actually, we cannot go up to omega. We go to omega prime, slightly smaller. So we build an extension operator, let's say, from a set B, which has a good boundary, up to some slightly smaller set omega prime, satisfying again the fact that it is an extension operator, that it is LP continuous, and then that gives this control on the increments of the extended function in terms of the original one. Here at this stage, we do not need any connectedness because here we do not restrict to a neighborhood of the boundary. This is not needed yet. And so the proof is, I want to thank Lorenza for sharing with me her slides of a previous talk, because the pictures are beautiful. I cannot do better. And then, so this is the situation. We want to extend essentially from B to omega prime. So this is, we want to reach all this area. But now it's better that I remove this, okay? So we assume that the yellow part is Lipschitz. And thanks to this, and thanks to Andrea Piatni's proof, there is a neighborhood, the yellow neighborhood hue, such that, and there is a, let's say, a map, a sort of reflection map that maps the part on the left here to the part on the right there, which is B-Lipschitz, by Lipschitz, and the Lipschitz constant depends just on that of the boundary of the set P. This construction is not trivial because a local map of this type exists at each neighborhood of each point, but to glue all together by a partition of unity and prove that the result is still invertible map requires some clever, let's say, tool. So this is true. So we have this mirror reflection. And then, okay, provided we take points only very close to the boundaries, so in this pink region, so that the inverse reflection remains inside our set, we define in this design region, in this pink region, our extension and then outside in this way. So we take a cutoff function that covers the closure of, it is equal to 1 in the closure of B, and is identically 0, let's say, out of B, but far from the boundary, so out of the pink region. And we want to extend from B to omega prime in this way. Inside B, we take the, let's say here, we do not change anything. We take the original function. Far from the boundary, we take a constant, which is the mean value, the average, integral average of the function u. And in between, we combine the two values with this cutoff function. So this is the, let's say, the definition, which is the same that is proposed with some adaptation, proposed by Braides and Piat in their paper. And then we prove the estimates. And the main ingredients are very simple, but require just some care. So just to prove, the first inequality is something standard that comes from the Hölder inequality, that you can estimate the integral of u minus its average by a double integral in this way. So UA is just, let's say, the integral of u divided by, it's the mean value. And then it takes care to estimate the double integral by, let's say, splitting our domain here, this domain, according to the positions of the points and taking, let's say, the value r smaller than this parameter t, so that only closed pairs of closed points are relevant. And then using Jensen's inequality and the properties of our function R. Okay, so that's done. And then the next step uses the connectedness. So now, essentially here, this step built the extension operator in the large for epsilon equal to 1. We have not yet epsilon perforation, but just perforation in a set. So we take a periodic set. The perforated set is just omega intersection this E, and we want to extend outside to omega prime, a set which is contained in omega, but slightly inside in order to exploit what we did before. And here the connectedness comes into consideration because we prove that, we are able to prove that the estimate is valid where on the right you have the possibility to reduce let's say, the neighborhood of the diagonal for any R, but paying a price that you may increase. You should increase the constancy too. Okay, so we use the previous step. So we use the fact that the perforated cell 3Q is contained in a nice set C, which is a connected component that has a nice boundary at the points that we need. And then we use our lemma, with previous lemma too, with extending from B, now it is this connected component, to the cell, the complete cell, non-perforated cell, omega prime equal the cube with side 2. And once we have this in our hands, we just move this construction, let's say, covering RD with an open cover of these cubes translated by integer vectors. And then in the end, we glue by a partition of unity. So we move all this extension, we sum up all of them. And in order to conclude, then we have this last step that we want to reduce again to the neighborhood of the diagonal. So the last step is the one that uses the connectedness of the domain. And to do this, essentially, we want to estimate from each cell the double integral with something on restricted to the diagonal. And the idea is that since the boundary of this connected component is Lipschitz at these points here, let's say in this part of the domain where we have this smaller cell, then for each 2 points inside the perforated cell, we can join them, staying inside a tubular neighborhood of, let's say, a path. So a union of balls of certain radius that remain inside the perforated big cell. And in the connected set. And then in this way, we can estimate the first integral with a finite sum of integrals on product of such balls. And the number of balls, of course, increases as the radius goes to 0, becomes smaller and smaller, but still we have a finite number of balls, and then we have a finite constant. So this is the technical step. And then the last step of the proof is just to introduce the parameter epsilon and to rescale everything. And since the estimates are separated, they rescale nicely, so they are preserved under rescaling. So first we adapt the previous lemma to the perforation. So here some E is missing. And also here, so this is epsilon E. And then we extend, for example, by 0 out of the retracted set. This is okay. So this is the end of the proof of the general extension theorem. And we can use this to study homogenization problems, for example, problems of this form. Now here the integral is written in a more general context. We have a double integral, so a non-local functional. Instead of having ux minus uy, I already made this change of variable for an easier notation. And the fact that the domain is perforated can be seen here. We have x inside the perforated set and also x plus epsilon psi in the perforated set. And now we take any let's say, function h with, let's say, Borel function, assume that it is periodic in the first variable, and have these growth conditions from above and from below that are the ones that we have studied before. So from above, we assume that it's bounded by some function times z to the p with this finite integral, and below, we assume the sort of coercivity condition. So under these assumptions, thanks to the previous result, even if we have perforation, now we can play the game as combining the two tools. We can put together the extension theorem plus the compactness theorem of the 5 authors, Alicandro, Ansini, Braides, Piat, and Tribuzio. So first, if we have, let's say, functions u epsilon, which has bounded norm and bounded energies, then we can extend them and then use the compactness result of the 5 authors. So the extended functions are relatively compact in LP for any omega prime strongly contained in omega, and the limit points are in W1P. So in a sense, we recover the setting of the classical case. And that's why the homogenization takes place in the usual sense. For such functionals, we can compute the gamma limit in the LP log topology and get the usual form, in a sense, a local functional, where let's say, if for simplicity we focus on the case of convex dependence on the difference quotients, the usual self-formula holds true, computed in this sense. The only remarks to be done is that here, when we compute this homogenization formula, either in the complex case, in the convex case, or in the general case, we always play with LP and not W1P functions at this stage. And then let's say the boundary condition here, for example, the Dirichlet boundary conditions must be understood. There is no trace for LP functions, so it must be understood as a condition on a set of positive measure. So it is imposed for the points that have a distance, for example, at most K0 from the boundary. Okay, so this is more or less what we did. And so the work in progress on this type of problems is in the direction of studying some non-local version of, for example, double porosity models, and non-local version of problem with more general growth conditions. So maybe PQ or variable growth, we do not know yet precisely, but let's say to exploit this result in some direction. So this is just the closely related references that I was mentioning before, this paper by Ansini and others, and that is going to appear very soon, and the paper by Braides and Piat. And thanks a lot for your attention.